Here is a quick check for prior knowledge for today's lesson. If you feel so inclined to answer these questions, let's suppose we have a book that's sitting at rest on a table. We ask A, what forces are acting on the book in this specific scenario? B, what types of energy, if any, does the book have? And C, is it possible to determine how the book got on the table just by looking at the book on the table as is? What do these seemingly mundane questions have to do with today's topic? Well, that's what we'll explore down the line in today's lesson. So today we're looking at gravitational potential energy and total mechanical energy, the topic for 4.3. Some announcements, or just one announcement better said. Unit 4 late work is due Monday, December 14th. All late work for Unit 4 is due Monday, December 14th. So what we're up to today. We are exploring and defining what gravitational potential energy is, and we're establishing the idea behind total, net, or net energy. All right. The same way that we talked about how all the forces acting on together could be summed, acting on an object could be summed together to give us a net force. We can add together all different types of energies that an object has to get the total energy. So gravitational potential energy. Okay. Gravitational potential energy is the energy stored in an object due to its height above a source of gravity. So in our case, on Earth, the source of gravity is, well, the Earth. So we would measure our height above the surface of the Earth. Gravitational potential energy, in fact, all forms of potential energy, not just gravitational, but also things like electrical potential energy as well, has a property called path independence, meaning that the amount of energy, potential energy an object has does not depend on the path taken, only the height of the object. So our equation for potential energy is potential energy equals mass times the acceleration due to gravity times the height above the surface of the Earth. Okay? We represent potential energy with the letter U, and then the type of potential energy with the subscript. So G in this case referring to gravitational potential energy. Okay? Path independence, again, the idea here is that if I lift an object up a height h, it's going to have the same amount of energy at that height, same amount of potential energy at that height h, regardless of whether I lifted it straight from A to B, whether I took it along this curved green path right here, or I did this zigzagging kind of sinusoidal path right here from A to B. Regardless of which path we take, the object will end up at the same height and thus will have the same potential energy. So that's why I asked that seemingly mundane question, can we determine the way that a book ended up on a table just by looking at the book? Is that we don't care about the path, we just care about, with regards to potential energy, where our object ends up at. So next, that helps us define total mechanical energy. Okay? So total mechanical energy represents the sum of all the total energies that a system can use. Any source of potential energy, as potential energy can be used and work can be done on that potential energy, to convert to kinetic energy, which allows our object to move. And then we have all forms of kinetic energy as well. And total mechanical energy is represented by letter E, E for energy, and it's equal to the sum of potential energy plus the sum of, or is equal to the sum of potential and kinetic energy for specific system. So for example, the total mechanical energy of a car starts off in strictly chemical potential energy. And then through combustion, work is done on the chemical energy that turns it into heat. And then the heat does work on a car engine that turns the heat energy into kinetic energy. So now by the time our car is moving, we have had some of our total mechanical energy turned into heat, and then the remainder turned into kinetic energy from the heat so that our car can move. And then in terms of specific equations, we can replace U with the equation for potential energy, which is mass times gravity, acceleration of gravity times the height above the surface of the Earth. And then we can replace K with the equation for kinetic energy, which is 1/2 mass times velocity squared. Okay? Please do not confuse, or please do not forget to square the velocity term in your kinetic energy equation. So let's do a quick think, pair, share here. Let's say we have a 200 kilogram airplane that's flying at an altitude of 4 meters at a speed of 30 meters per second. We ask what types of energies make up the what types of energy makes up the mechanical energy of the plane, and then how could we use the information in the prompt to determine the total mechanical energy of this object. So we can take note the plane is rotational kinetic energy from the blades rotating, is translational kinetic energy as our plane is going to move from one location to another. There's gravitational potential energy in the fact that our plane is a certain height above the surface of the ground. And there's also chemical potential energy in the form of chemical bonds in the gas in the car engine. Now, with regards to plane engine. Now, with regards to B, how could we use information given to determine the total mechanical energy of this object? Okay, so we know total mechanical energy is equal to the sum of potential and kinetic. We know potential is equal to m times g times h, and we know kinetic is 1/2 mv squared. We know what g is. G is 9.81 meters per second squared, which we can round up to 10. We've been using that since beginning of the year. We need to know the mass and the height and the speed here in order to calculate our total mechanical energy. Well, we know the mass is 200 kilograms. We know the height is 400 meters, and we know the speed is 30 meters per second. So we can plug that information into our equation here in order to determine our total mechanical energy, which is going to be 800,000 joules, which is a lot of billijoules. That's a lot of we didn't start the fires. 890,000 billijoules. Okay? And if you're wondering why we're taking baby steps here of just plugging in numbers, it's because we're going to tie this all together with a very abstract topic at the end of the week where we look at conservation of energy. So we're taking baby steps now to make one big giant step at the end of this week. So now let's do a check for understanding. A 1,200 kilogram car is moving on the ground at a speed of 13 meters per second. We ask A, does a car have gravitational potential energy? And we can assume that we're measuring from the ground. Some of the more astute people in the class might notice, or more observant people in class might notice, that we could choose to measure our heights from different objects, and that the potential energy in this case would depend on where we measure our height from. In this case, we're going to measure our height from the ground. So our car is on the ground, we measure our height from the ground. All right, and the car is moving at a speed of 13 meters per second. We ask A, does the car have gravitational potential energy? Why or why not? So relative to the ground, no, the car does not have gravitational potential energy because it is not located at a certain height above the ground, thus has no potential to be in free fall. And again, as people rightly noted, well, what if this was actually a hill right here? Then yes, we would say the car has gravitational potential energy because it has potential to fall. But again, that all depends on what you're measuring your height relative to. In this case, we measure our height relative to ground, so we have no gravitational potential energy. And then we ask, what is the total mechanical energy of the car? So total mechanical energy is going to be equal to the potential energy plus the kinetic energy. We don't have any potential energy, so we can cross that out and make it equal to 0. So you get that the total mechanical energy is strictly equal to the kinetic energy of the car, or equal to 1/2 mv squared. So we plug in our knowns, 1/2 times 1,200 times 13 squared. We square the 13 first, and then we multiply by 1/2 of 1,200, and that gives us a total mechanical energy is 100,000 or 101,400 joules, which is a lot of billijoules. And this is our main lesson on total mechanical energy and gravitational potential energy.